Okay, in this video we'll be talking about satellites and circular motion. You have a satellite above the Earth's surface at some fixed orbit, some distance r from the center of the Earth out to where the satellite is orbiting. There is only one speed that the satellite can have if the satellite is to remain in that orbit. And when it is at that orbit, the force of gravity pulling the satellite into the center of the circle, the gravitational attraction between the two, must be equal to the centripetal force. In other words, you've reached equilibrium. Okay, so the sum of the force are equal to the centripetal force. The centripetal force is equal to the force of gravity. Centripetal force is equal to the force of gravity. And if we solve for v, we could find the speed that this occurs at. So how did we get this? Now let's take a second to look at this. Alright, notice the m's cancel from both sides. Okay? This r canceled with one of these r's. And then with g, I'm left with g me over r equals v squared. And if I take the square root of both sides, I end up with v is equal to square root of g, mass of the Earth over the radius. And it's really kind of important to understand that the mass is not needed. This means, like, if you were out, say, for example, on the space station, and you walked out of the space station in a spacesuit, even though you have a different mass than this space station, you would have the same equilibrium as a space station would. Because at that particular velocity, whatever velocity of the space station you were going at, you're in balance with the gravitational force. Alright, so here's an example. Determine the speed of the Hubble Space Telescope orbiting at a height of 589 kilometers above the Earth's surface. In other words, what speed must it be going at to maintain that equilibrium between the centripetal force and the force of gravity? So here's the equation we just derived. You put the numbers in for big G, the mass of the Earth, and now for the distance between them, I had to take the radius of the Earth plus the height it was above the Earth. So this is how fast it has to go, about 17,000 miles an hour, to maintain that equilibrium. Okay, but what if we wanted to solve for the period of rotation at this orbit, or even the radius at this orbit? Alright, well, we know from our equation before that velocity is equal to this term, this expression, the square root of universal constant times the mass divided by the distance between the two objects. But we also know the velocity is equal to distance over time. And we know the distance going around the circle is simply the circumference, and the time to go around the circle is simply the period. So we can actually set this expression equal to this expression. And let's try to get rid of that square root. Alright, so I squared both sides, and I got rid of the square root on this side, and now the 2 becomes a 4, the pi becomes pi squared, r becomes r squared, and period becomes period squared. Alright, and now what I'm going to do is try to combine terms, like for example these r's are here and here, and so I'm just going to rearrange it a little bit. And here's how I rearranged it. Is I brought the period squared on the top, the g me on the bottom, and I moved this r up there. Okay? So now I have an expression for period squared. To find an expression for period, I had to square everything. And if I take the square root of this, it becomes 2, the square root of this becomes pi, square root of this becomes 3/2 r, and the square root of this is, well, square root of it. I could also take this same expression here and solve it, if I wanted to, for the radius. Okay, so what do these two expressions really give us? Really, if we know the mass of a satellite, the planet that the object is rotating around, for example, in this case, the mass of the Earth, and we know the period of rotation, we can figure out what altitude it has to be at. Now this isn't actually altitude, it is the radius plus the altitude when you think about it. In other words, this distance is from belly button to belly button of the two objects. And here is the exact opposite. If you know the radius and you know the mass, you can figure out the period. Okay. Now what's kind of interesting about this is, once again, you do not need to know the mass of the satellite. Okay. So can we place a satellite so it remains in the same position all the time? And the answer is simply yes, as long as the period of rotation is the same period of rotation as the Earth. And this type of satellite is used like with like DirecTV, so that your satellite dish in your house is always pointed up to the satellite, and the satellite's in the same location all the time. And it's really not in the same location, but it happens to be spinning at the same rate the Earth is spinning. All right, now I'd like to talk about weightlessness and artificial gravity on satellites. All right, so we know that if you're like in an elevator car and the cable snaps and you're standing on a scale, the scale will read 0 because you're in free fall. But what would the scale read if you were in the space station and it's in orbit, okay, and you stood on the scale? What would it actually read? And the answer is they would both weigh 0 because they're both in free fall. Now that may seem confusing because it doesn't seem to be falling, the space station, but it actually is. It's falling at the same rate the Earth is curving out from underneath it. So let's say it falls close to half a mile. In the time it takes to fall a half a mile, the Earth has actually curved out from underneath it a half a mile. So it's staying the same height above the Earth as it falls. So it is in a continuous state of free fall. Now, if you're in the space station for a long time and you have this free fall situation and this weightlessness situation, there are some problems with that. You would have muscle deterioration and other health problems. So maybe it might be kind of nice to have some type of artificial gravity on these space stations or future spacecrafts. And how can we actually do that? Well, the next couple moments we'll talk about that. How we can actually do it is spin it. All right, so here we have a space station. All right, and if we spin this, we can actually get the floor to push on the bottom of the guy's feet, just like it feels like the floor on Earth would be pushing on your feet. Now, as long as its space station is spinning at the correct speed, you can actually create a feeling of gravity just like you have on Earth. It's called artificial gravity. So let's try a problem like that. At what speed must the surface of the space station move so that astronaut experiences a push on his feet equal to his weight? Now that's assuming the radius of the space station is 1,700 meters, which is a pretty decent size, and this is not drawn to scale whatsoever. Okay, so what we're trying to do is we're trying to set the centripetal force equal to your weight. And we know that centripetal force is just equal to mass times V squared over R. We're setting that equal to your weight. And notice once again that it's mass on one side and mass on the other. The masses cancel out. So we can actually set an equation up where we can create factors of G, or factors of gravity. In other words, we can actually sit there and say, well, how much of Earth's gravity do we want to feel? All right, so in this case, they wanted to feel 1 Earth gravity. So if you solve this for V, V would be equal to RG, and here's the radius, times R, take the square root of it, and you would have to spin this thing at 130 meters per second to create the same feeling of gravity as you would feel on Earth.